Good morning, everyone. My name is Kaibin from Swinburne University of Technology, and today I'll present my paper named Hourglass, enabling efficient and split federated learning with data parallelism. So I will present this paper as the following 6 parts, and include the backwards limitation of the split FL, the Hourglass, the evaluation, Hourglass overview, and the conclusion. So in the past few years, federated learning has been as a promising solution to train machine learning models with privacy preservation, and it often goes through 4 parts. First, the client training their local models on their own datasets, and then it go to step 2, transfer the local models to the Fed server, like the cloud server or the edge server. After receives of the local models from the client, the Fed server will aggregate of the local models into the global models, and they often use like the Fed average method by averaging the model parameters of the local models. So finally, in step 4, the Fed server will transfer the local model of the global models to the client for the next training. So in this case, compared to the cloud-based scheme and in federated learning, the only machine learning models exchange between the client and the Fed server. So in this case, the federated learning protect the data privacy. In recent years, research has proposed some high-performance machine learning models like the VGG or the ResNet or the VIT or Transformer. And all of these models comes in large size, as illustrated in Figure 1, and we can get the Dino V2 reach the 99% of the top 1 accuracy with over 1,000 million parameters on the CFR10 datasets. So in this case, if federated learning want get a high performance for the global models, the client must deploy and train machine learning models with a large size. But in practice, the client, like the mobile device, they do not have they just have the limited capacity, like the processing unit or the memory. So in this case, federated learning cannot get a high performance under limitation resources for the client. To address the above challenges, some research propose a split FL. In split FL, a model is sliced into 2 partitions, client-side models and server-side models. The client-side model is deployed on the client, and the server-side model is deployed on the Fed server, and it often goes through 5 steps. The first step is the client first trains the client-side model on their own datasets, and then transfer the intermediate feature to the Fed server. After receive the intermediate features, the Fed server trains the client server-side model partition, one for each client, based on the intermediate features, and then transmit the intermediate gradients back to the client to update the client-side model partition. And finally, the Fed server aggregates server-side model partition to produce a global server-side model partition for the next training round. And in this case, the split FL removes the most of the workload from the client to the Fed server. So in this case, the federated learning can train a larger-sized machine learning model to reach or to get a higher accuracy or higher performance. But it also faces some limitations. The first limitation is computational overhead. When there are a lot of clients in the machine learning system of FL system, the Fed server may not able to allocate 1 GPU to train each client server-side models. For example, let's take a look at the image. In this Fed server, there are only 3 GPUs, but the Fed server need to train a 10 server-side model. So in this case, Fed server cannot allocate one single GPU for each server-side models, and in case it need to share available GPUs across all client, but it brings some extra switching time. Here's an example in the image. One GPU need to train 2 server-side models. So first, after training one server-side models, the Fed server need to switch it out to the GPU and load the next server-side model into the GPUs for the training. Sharing GPUs across the many clients requires a switch time, and this can incur a significant communication overhead because switching our machine learning models, especially for the transformer or the VIT, out of a GPU takes a lot of time, and as illustrated in the table, and we can get the switch time is from 30% to almost 80%, 13% to almost 80% of the overall time to make the global model to achieve target accuracy. So actually, this switch time is huge and unacceptable. And another limitation is storage overhead. The Fed server must maintain a server-side model partition for each client before the Fed server aggregates this server-side model into a global model. So when there are a large number of clients, in some cases up to millions, the Fed server need massive storage capacity to share their server-side model partitions. So to address the above 2 challenges, we present Hourglass. In Hourglass, there are 2 configurations for the Fed server. 1 GPU means the Fed server only have 1 GPU, and the multiple GPUs means the Fed server have multiple available GPUs to train the server-side model. So the root reason for the computation and the storage overhead is the Fed server need to maintain multiple server-side models, and one for each for the end clients. So we think about we can maintain one shared server-side model for all of the clients, because in the one GPU, and we just want maintain one shared server-side models for the client. So in this case, a Fed server do not need to swap in and swap out the server-side model and save the waiting time. And let's take a look at the right image, and we can compared to the maintain multiple models, maintain single models, accelerate the model convergence and the top one accuracy. And let's take a look at the right image of the experience, and we ignore the switch time. The switch time is the red bar, and we ignore the switch time, and we just focus on the computation time with the green bar, and we can find even though we ignore the switching time, the single model still better than the multiple model. So this tells us by training a shared server-side model partition, it achieves more efficient knowledge fusion compared to the classical split federated learning system. It is well known that data heterogeneity is a common issue in federated learning, because the different clients have different preference, have different habits, and so we thought, is there any difference that trains the server-side model with a different order of intermediate features? So we propose the two intermediate features scheduler strategy named similar feature first and the dissimilar feature first. For the similar SFF, like the left image, we want to make the similar features closer. So in this case, and then follow the order to train the server-side models. And basically the native ways is randomly select the intermediate features, but it is not our contribution. And about the DFF is let's take a look at right image, and we're trying to make the dissimilar feature closer, and we do some experiment and find the performance of DFF is better than the SFF. The reason is the SFF adjust in a specific direction for the machine learning models and potentially trap the model in a local optimal and reduce the generalization capacities. So how about the multiple GPUs? And the multiple GPU configuration, it means the Fed server has a multiple GPU, available GPUs. Like the left image, the Fed server has 3 GPUs. So in multiple GPUs, we maintain multiple shared server-side models for all of the client based on the number of the available GPUs. So in this case, the Fed server need to maintain 3 shared server-side models, and in this case, similar to the single GPU configuration, there's Fed server does not need to swap in and swap out the server-side models. So in single GPUs, we trying to make the dissimilar features closer. So follow based on the advantage of single GPU configuration. In the multiple GPUs, we also trying to make the dissimilar features, intermediate features in the same GPU for the server-side training. So in the multiple GPU, the scheduler will use some clustering method to group the similar intermediate features into the same cluster, and then distribute and then assign the intermediate features to the server-side models for the next training. But we find But we find the clustering method, like the k-means, takes a lot of time because the intermediate feature is a higher dimension data. So and we also conduct the experiment and find the clustering. In this case, we use k-means to cluster the intermediate features, and we can find the clustering time is from the 8% to 24%. It's not very huge, but it's not very huge, but it exists, and we need to figure out the things. So we introduce LSH. The LSH use a hash function that map the data point into the buckets, such as the nearby point have a higher probability of sharing the same hash values. Here's the example. There are 5 data in the right image, and the data with a similar color means they have the similar distribution, and the data goes through the hash function and go into the different hash buckets, and we can get the data. The similar data will go to the same bucket. So in this case, and we can use LSH to cluster the data into the different groups. So compared to the k-means clustering, and there are 2 advantages of LSH. The first is LSH can efficiently approximate the similarity between higher dimensional data points. And the second is LSH can assign data points to buckets individually without the need for the entire dataset. Here's an example. For if we use the k-means, the clustering method. Before we start use the process the k-means clustering, and it need to offer the data. We talk about their data heterogeneity in federated learning. Actually, there are also some resources heterogeneity in FAL system, and like because the client have a different heterogeneous resources. So in this case, the time that the intermediate feature arrive at the fed server is different. So if we use the k-means method to cluster, the k-means to cluster, the scheduler have to wait of the intermediate features arrive at the fed server and then process the clustering procedure. But the LSH do not need to wait for the entire datasets. So this is the second advantage of LSH compared to the k-means clustering method. So here is multiple GPUs configuration for the Hourglass, and after the intermediate features arrive at the fed server, and the scheduler will use LSH strategy to distribute or assign the different the intermediate features to the buckets, and then distribute the intermediate features to server-side models. And we also do conduct some evaluation because the limited time, so we just ignore the evaluation. Okay, the result is great. Yeah. So let's recap the Hourglass overview. And here is a multiple GPU configuration, and the client transfers the intermediate feature to the scheduler of the fed server, and the scheduler use LSH strategy to distribute the intermediate feature to the server-side models, and then training the model. Finally, the aggregator aggregates the server-side model into a global server-side model for the next training round. So let's conclude the Hourglass, and there are three contributions of Hourglass. The Hourglass, instead of maintain a server-side model partition for each client, the Hourglass only maintains the server-side model partition based on the number of available GPUs, and we present a new dissimilar feature first strategy. Hourglass achieve a top performance in model convergence and model accuracy. Finally, the last one is Hourglass use the LSH to cluster the client intermediate feature to accommodate practical scenarios where the stragglers can easily slow down the entire training process. So thanks a lot for your attention.